Okay, so we're going to pick up where we left off with a quick review of summarizing continuous variables, and then we're going to actually do simple linear regression, which is what this class is all about, and then we will start on the lab. So the learning objectives for this part, we're going to hopefully be able to recall how to summarize a single continuous variable, be able to identify variables where the mean is a good summary measure or not, and then finally be able to sort of describe like the big picture, what we're all trying to do here. So at the end of class last time, Mark, right? Yes. We were able to sort of try to brainstorm a little bit why we do statistics, and you all sort of put the type of thing that I was hoping you would. It was a lot about pattern recognition, ways to understand data, ways to summarize data, ways to help to make decisions. So the big picture here that I was trying to sort of get across is that essentially often with statistics we've got something like several pieces of information that we're trying to distill into fewer pieces of information to help us make a decision. And when doing that, we basically make assumptions in order to take many data points and distill them down into one or two data points. And so today we're going to be talking a little bit about kind of what those assumptions mean and why we make certain assumptions and when they may or may not mean that the summary measure we calculate is representative of the full data that we're trying to explain or understand better. So let's start with a single continuous variable. This should very much be a review of things that you've probably seen in previous classes. But how can we visualize a single continuous variable? So when we were talking about visualization last week, what types of plots did we do when we were trying to visualize just one continuous variable? What's it? Histogram, yep, that's one. Box plot, that's another one. There's one more I think that we did. Was it histogram? Yep, so we got that one. Histogram, box plot. There's one more.
Density chart?
Yeah, density chart, exactly. So these are sort of the three main ones that we use often. Oh, and I wanted to mention for the going forward, when I include any output in R, you can, if you're interested in the R code that generated them, you can click these little code buttons. If the code is like pertinent to the thing I want you to learn, so like if I'm actually talking about R, then I'll make sure to print the code on the slide directly. But if it's just sort of incidental, but you happen to be interested in knowing how to make a plot or get some certain output, like what I have on the slide, you can click these little code buttons. And anytime there's code, you'll see this little clipboard in this top right corner that you can click on, and it'll copy the contents, and then you could paste that into R yourself if you were interested. Okay, so the three main ways that we visualize single continuous variables: histograms, density plots, or box plots. And how could we numerically summarize a single continuous variable? What do you calculate? There's a fly in here, I see it. What would be, like how were we summarizing data in class on Tuesday? What were we calculating? Mean, yeah. So in R, you can use the summarize function to calculate the mean. And this is, it's not a perfect representation of every observation, but it gives you some sense of kind of how, of what on average or a typical value would be. So for example, here I'm taking the Star Wars data, which consists of 84 Star Wars characters, and I'm calculating the average height. And so rather than showing 84 different numbers, I'm just showing you one to let you know that on average the characters in this particular data frame have a height of 174 centimeters. So I could put that on the histogram, and in this particular case, this is like a pretty good summary measure because it falls kind of in the middle. And this is a unimodal distribution, meaning that there's only one mode, and the mean kind of falls right along that mode, meaning that it's a symmetric distribution as well. And so this is a case where the mean is probably a pretty accurate representation of a typical character in this particular data set. So why do we calculate the mean? What are the goals when we're calculating the mean of something?
View of like normality or typicalness of the data.
Yeah, to get kind of some view of a typical value in the data. Exactly. So, one goal might be to reduce the dimensionality of the data. So if instead of like handing you a piece of paper with 84 numbers on it for all the different heights, I can just tell you the single number. So it reduces, in this case, the dimensionality from n, since there are n observations in a data set, to 1, since we're just reporting a single parameter, in this case, a mean. And the other is exactly as you said, to get a sense of a typical observation. So when will this be an accurate representation of an observation?
Normal distribution.
Yeah, if it's normally distributed, or even kind of more broadly when it's symmetric. So even if it's not normally distributed, as long as the data is symmetric, the mean will typically be a good kind of indicator of a typical observation. So here I've drawn 3 different distributions. I've generated some data in R. If you're interested in generating data, you can use this type of code. But what I've done here is I've generated a symmetric distribution for this variable x. Here I've generated a bimodal distribution, meaning there's 2 modes, and here I've generated a skewed distribution for x. And so can you guess the mean for each of these? What do you think the mean is for this first one? 10, yeah. And what about for the second one? 15. And what about for this third one? Yeah. Yes, I've heard a couple different. I think it's probably going to fall somewhere around 0.3. This is an example of a skewed distribution where the mean is going to be getting pulled a little bit to the right by this tail over here, so it won't fall exactly here at the center, but maybe a little bit to the right, so maybe somewhere around 0.3. Yeah, so good guesses, everybody. That was very good. So in which of these cases does the mean value represent a typical observation?
Symmetric.
Yeah, so in the symmetric case, for sure, it definitely, the place where there's the most mass in this picture, where the kind of most of the observations fall, is right around the mean. So this is a good, if you had a variable that looked like this, the mean would be a good representation. Which one is it the worst? Yeah, bimodal. So in the bimodal case, there are literally 0 people who have a value at the mean. It's representative of absolutely nobody in the distribution. So when you have bimodal data, the mean is a very misleading or kind of useless summary measure because it doesn't actually tell you anything about anyone in this data set. And then the skewed, this is like where data science becomes a little bit of an art because in this particular case, depending on how skewed it is, would dictate basically how meaningful that mean is. And so here, the mean is definitely a little bit to the right of kind of the hump of this data, but it's not pulled so far that there's like no meaning. I think you can get some information from this mean here. But if there was like a really big outlier, for example, an influential point that really pulled that mean really far away from the center of the data, then this would become less meaningful. And so if I were looking at these distributions and I were trying to decide what summary to use to calculate them, I would feel very good about a mean in the first case, I'd feel very bad about a mean in the second case, and I'd feel kind of mediocre about a mean in the third case. I probably would still calculate a mean in this third one, but if it was much more skewed, I would think about using something else like a median to represent the data. Okay, so putting this in kind of mathematical notation, I wanted to introduce the type of notation that we're going to be using in this class. This might be really familiar to some of you. I remember when I first started in statistics, like this sigma was foreign to me. I hadn't seen a lot of this stuff before. So I thought I would just take a second to step through it. And so this, on the left-hand side of this equation, I have x bar. And so a bar on top of a variable means that you're taking the mean or the average. So what I'm saying here is that the mean of the variable x is equal to the sigma, this thing that kind of looks like a big E. This means that we're going to add up observations. And so sigma is a Greek indicator that anything to the right of it is going to be summed up. And underneath the sigma, it tells us where we're going to start summing. And so in this case, I equals 1 will be the first observation. And then the top indicates how long you're going to sum. So n is going to be till the final observation. So we're going to take from the first observation to the final, we're going to sum them up. And then xi means the continuous variable for observation I. So the value for x for observation I. And then n, we're going to divide by the total number of observations. And so all this is the definition for a mean, which I'm sure you all are familiar with. When you're taking the mean of something, you just add up all of the observed values and divide by n. And so this is just the mathematical way to write that out. And we'll be using this type of notation a lot in this class. Okay, so quick application exercise. Here I have a little data set, and I want you to just answer 2 quick questions. First, using the data to the left, what is n? And second, I want you to answer what x bar is. I'm going to lower this time just a little bit because I don't think it'll take that long. So you can use the equation from before or just how you know how to calculate a mean and do that for these data points, and then think about what n is. And we'll come together in a second to discuss. Okay, so for these data, what is n? 5, and how do you know? Yeah, because there's 5 observations, yeah. And what is x bar? 4.8, yes, and you just got that by adding up 24 and dividing by 5. Very good. All right, so from our very first class, I showed you this little equation that basically sums up most of what we're doing in statistics, where we're taking some observed data and we're setting it equal to some model of interest plus some error, because the model never is going to fully represent exactly what the data say. And so we can put that same formulation into when you're calculating a mean. So here, my data are these x values. I here indicates the observation 1 to 5. So I have these 5 x values. My model here is that I'm just fitting a mean. So I'm estimating or I'm guessing what each of these values would be. If I were to see a new value of x, the best guess that I would have based on this model for what that value would be 4.8. And then the error just indicates how far off I was in each case. And so this error term, or sometimes we call this a residual, is how far off the model is from the observed value x. So for example, this first one, we observed a value of 3. My model guessed that it would be 4.8, so my error or my residual was negative 1.8. And similarly for the next one, we observed a value of 5, and so my model said it was 4.8, so my error is 0.2. So I could plot this, and this is going to build up, hopefully, to sort of make more sense as we're going forward, to try to connect what you've probably already done in statistics to what we're about to do with simple linear models. But we could plot these 5 values, so I've just plotted them here. So we have those exact same values here plotted. I've got my x, I have x along this axis here, and I've drawn a line at my model where the mean is 4.8. And then I could draw those, how far off those that value is. So those error terms or those residuals would be how far off each of my observed points are from my model or my guess at 4.8. And the thing about a mean that's nice is that that mean is basically the value that actually minimizes these distances. And so it turns out that if you summed up all of these residuals, you'll always get 0 if you use the mean as your model. And so we could take all of these error terms and sum them up, and we would get 0 as our sum because we used the mean as our estimator. So we could write this, putting this back into sort of math speak, we could write it like this, where our data here is x, those are our observed values, and that is equal to beta 0, which is what I'm going to call my mean that I've estimated, so in this case that 4.8, plus some error term. And so x here is actually a vector of values from x1 to xn, and so in our case, it would be those 5 values that we observed. And beta 0, this is, we call this the intercept when there are no other variables. It's just the mean, that x bar. And then epsilon is going to be my error term. And so kind of this line here is that beta 0, and it's where the intercept, where we intersect with the y-axis here. It's that 4.8. And then each of these distances between my observed points and my model, or this, in this case, just an average, those are my epsilons, or my error terms. So I could rewrite this as x here is my observed data, beta 0 is my mean, and then the error term here is this 1.8, negative 1.8, 0.2, etc. Okay, so to calculate the mean in R, we already have done this one way. So in class last time, we used the summarize function, where the first argument was the data set, and the second argument would be what you would like to calculate. So in this case, a mean. And I could get that 4.8 like you all did in that quick application exercise. Another way to do this would be to use this LM function, and this is going to be what we're using to fit linear models. And so here, the variable to the left of the tilde is the thing that the data that you're trying to predict. And so in this case, we were trying to estimate x. And the thing to the right would be the variable you're using to estimate it, which in this case, we're not using another variable. We're just trying to calculate an intercept. And so I can just use the number 1 to indicate that. And you'll notice I get this 4.8, exactly the same value that I got when I calculated the mean. And so this is known as an intercept-only model. That LM stands for linear model. And basically what I'm trying to do is draw the connection between what you're already familiar with, hopefully from previous classes when we're calculating a mean, and sort of extending it to what we're doing in the simple linear regression setting, where we're going to be, instead of just using an intercept-only model, we'd be using another variable to try to estimate the value of whatever is to the left of this. Okay, so what I want you to do is open your 04 apex.qmd file. This is the one from last class, and load the packages by running the top chunk of our code. And then I want you to copy this code below into an R chunk at the bottom of the file. So this is going to create a data frame. You would have just seen this you would have seen this in the check-in last night, but you can try typing $Tibble into the console to see what this function is actually doing. And then I want you to take this and calculate the mean of x using the summary function and also using the LM function. And then add a new variable called error to the data set D that is equal to x minus the mean of x. So I'll give you a couple minutes to work on that, and then we'll do it together. And again, anytime you need to copy code from the slides, you can click this little copy button here at the top, and it'll copy all the contents of that if you don't want to have to highlight it. All right, let's start doing it together. So I'm going to log into RStudio Pro and make sure that I'm in that 04 application exercise project. And so I can tell that I'm in the right project because up here on the top, I'll see the name of the project I'm interested in. And you click on files, you'll be able to see those files. And I'm going to click this 04.qmd. I'm going to load this. And while that's loading, I'm going to start typing the next part. And so the first thing I wanted you to do is copy this code here. Can anyone tell me what a tibble, what this function does? Yeah.
Constructs a data frame.
Exactly, it constructs a data frame. And so the tibble function it's very similar to the data frame function, but tibbles are data frames, but with some extra kind of pizzazz in that when you print a tibble, it'll give you a little more information. The typical data frame wouldn't have information about the number of rows and columns, and also wouldn't print information about things like the variable types. And so the tibble just has a little bit of extra things like that. If I typed $tibble here and I click on this top one, I can see information about how this says it constructs a data frame. And after running that, you'll notice I have this data frame called D up here in my environment, so that worked as well. The reason why it's called tibble, I don't know this for sure, but Hadley Wickham is the developer who created the package that this comes from, and he's from New Zealand, and when he says the word table, it sort of sounds like he's saying tibble, and I think that's why it's called tibble, although I've not actually asked him. I should ask him. Okay, so we've got our tibble. How would I calculate a mean using the summarize function? Yeah, exactly. And so this told me that the mean is 4.8. Very good. And if I wanted to do the same thing using a linear model by fitting an intercept-only model, what would I do? Tilde 1. Data equals D. And I get an intercept here of 4.8, so the same thing. And if I wanted to create a new variable that was the residual or the error between this model and the actual observed values, what would I do? If I want to add a variable to the data frame D, what function could I use? Mutate, yeah, that's right. And so if I wanted to call this error, how could I calculate the difference between the observed x and the mean value of x?
Mean of x minus x.
Yeah, I think I would probably do x minus mean of x, but both will get me just the inverse of them. Yeah. Yeah. Great. And so that got me the error. If I wanted, you'll notice that if I look up here, this object D still just has 5 observations and 1 variable. And so all this did was output a data frame with those 2 variables, but I haven't actually saved it. If I wanted to save this as something, what would I do? Yes, the arrow, exactly. I could assign it to an object, and I could even overwrite this object D and have it now have 2 variables. And so now if I look up in my environment, I notice that D has 2 variables, x and error. Are there any questions so far?
Can you scroll up for a second?
Yeah. All right. Okay, great. So the big picture here is that the mean is an appropriate summary measure to calculate when you have a symmetric distribution. And so basically the assumptions that need to be true in order to use the mean to represent your single continuous variable are that the mean will actually be representative in some way so that, it's actually a meaningful metric. So now we're going to upgrade to 2 continuous variables. So now that we've discussed how to summarize a single continuous variable, we can summarize the relationship between 2, which is what simple linear regression is doing. And so if I want to visualize 2 continuous variables, what would I do? What kind of plot would I make? I think I heard you say it. Yes, a scatter plot. Yes, a scatter plot. So here we've got a scatter plot. On the x-axis, I have height. On the y-axis, I have mass. This is the relationship between height and mass in the Star Wars data. You can look at the code here. I have dropped one observation from this data set. I've dropped Jabba the Hutt because he's got a really big mass, and so he skews the picture. So for these, I've dropped him from my picture. And so I could use something like this to try to help me answer the question, if we knew a Star Wars character's height, can we guess how much they weigh? And so I might use some information about the height and weight that I've seen for these observed values to help me guess how much a new character might weigh, given I knew that their height was a certain value. And so coming back to that same data equals model plus error, we can use this same metric to be able to try to answer that type of question. For now, we actually have 2 observed variables as opposed to just having the one. We have y and x. And so in the simple linear regression case here, y is going to be a continuous dependent variable, and x is going to be a continuous independent variable. And that's because y is dependent on x here in the way that we formulated this question. And f of x is going to be a function that gives the mean value of y at any value of x. And so what function do you think we're using to get the mean value of y when we're doing simple linear regression? What is it? Also a mean? Is that what you said? Yeah, we're going to be using a line. So we're going to fit a line between our data. That's going to be our mean function. And that's how we're going to estimate the average value of y. So for any value of x here, for any value of height, we could guess the mass by using this line as basically our model to help us estimate it. And so for simple linear regression, the function is just a line. So you could say this, we express the mean mass of Star Wars characters as a linear function of their height. So thinking back to your last stat class, what is the equation that represents this line? Y equals mx plus b, exactly, yes. So in like regression space and kind of the broader statistical world, we replace the m and the b with these Greek letters, which is basically because then it will extend easier when you have more variables. Instead of needing to have like new letters, you can just index your beta. These are called betas. You can index them with numbers. And so that m from y equals mx plus b is written as beta 1, and the b is written as beta 0. But this is the exact same equation that you're used to seeing previously. And so we could write this as, for example, mass equals beta 0 plus beta 1 x height, where beta 0 is the intercept of this model. So it's going to be where x is equal to 0. And beta 1 is the slope of this line. Okay, so if I were trying to interpret what beta 0 means, what would that be? How would you, in words, describe beta 0? The intercept, yeah, and kind of in terms of what that would mean in this particular problem, it would be the estimated mass for a character with a height of 0. And so in our actual observed data set, we don't have anybody with a height of 0, so you don't actually see the intercept. You'd have to kind of continue drawing the line, but because it's just a line, you could extend it infinitely in either direction. So we could draw it all the way to 0 and figure out where that beta 0 or that intercept of this model is. Now in this particular data set, is this a meaningful value? No. Yes. No, it is not. Because it's not practical to have a height of 0, and similarly, it's not practical to have a mass of like negative whatever this is, 30-something. And so this is not a terribly meaningful result. It's useful so that we can draw the line, but it's not really an interpretable value since that's not of practical use to us. There are some times where your x variable, knowing the value of y or the average value of y when x is 0 is meaningful, but in this particular case, it's not. But it's good to know kind of what that value actually means practically. Okay, what is beta 1?
Slope.
The slope, yeah. So what that means is if we increase 1 unit in height, which in our case is a centimeter, so for every 1 centimeter increase in height, how much do we go up on the in mass or on the y-axis? So that beta 1 is just going to measure the increase here relative to a 1 unit increase in your x. And so again, this is important to keep in mind what your units actually are since they matter. So here, height is measured in centimeters. So 1 unit increase is 1 centimeter. If height were measured in meters, then the way you would interpret what that beta 1 is would be different because it would be a much different number because it would be based on a meter increase as opposed to a centimeter increase. So keeping in mind the units is important when interpreting these coefficients. So that's our estimate, that line, but of course the actual observed data points, like we saw when we were calculating the mean, don't fall exactly on the line. And so that's where that error term comes in, where it shows the deviation from this estimated model for the actual observed data points. So for example, I could draw those same types of lines here, and those would be the error terms or the residuals, the difference between the observed points and the actual value y. Okay, so a little bit more on math notation. The truth or the true, when you're trying to estimate the true model, or when you're trying to discuss the true model, the thing that we're actually trying to estimate, it's going to be like this. It's y equals beta 0 plus beta 1 x plus epsilon. And so these betas are like the true betas in the full population. So if we had the whole population in the Star Wars universe, we could actually quantify the exact relationship between x and y. And so x here is our observed x, what we actually see in the data. Y is our observed y. And these betas, as they're written here, are the true relationship between x and y, like in the whole population. So these are the parameters that we're trying to estimate. The truth, and I'm going to switch to Chrome. For some reason, the little hats look better in Chrome than they do. There we go. So the little hats indicate that we're estimating something, and this is actually the reality. So in reality, we just have a sample of Star Wars characters, and we're trying to estimate the relationship between x and y, or height and mass. And so you'll notice x doesn't have a hat, and that's because that is the true observed value of x that we're using. But everything else has a hat because it's an estimate. And so we're basically estimating what we think those beta parameters are in the true population using our observed data to get an estimated value for y, or what we would guess the mass is based on that height. And so those hats represent estimated or fitted values. So this is sort of important. Like basically when you don't have hats, when these parameters don't have hats, then those are kind of the goal or the thing we're trying to estimate. When we're actually estimating values, they'll have little hats on them. So the way you can tell the difference between a parameter that's from the whole population versus an estimate from a sample is the estimates will have these little hats on them. And this is increasingly important as you go on in statistics to sort of be able to distinguish between the two. Being able to kind of notationally distinguish between what the goal is and what you're actually estimating in the data, those are often two different things. Okay, so another pause for definition. So the parameters that we're estimating in simple linear regression are beta 0 and beta 1. Can someone tell me what beta 0 actually is? The intercept, yeah. And what does that mean, like in terms of the observed x value?
The expected value of y when x is 0.
Exactly, the expected value of y when x is 0. And what about beta 1?
The expected increase in y for every value in x.
Yeah, the expected increase in y for every 1 unit value in x, or the slope. Exactly. And so then the simple linear model is just this y equals beta 0 plus beta 1x plus epsilon, which is estimated by this y hat equals beta hat 0 plus beta hat 1x. Okay, so let's do this in R. To do the first, I'm going to use the Star Wars data, but again, for this, I'm going to delete the values where mass is greater than 1,000, which is just the ones. I'm removing Java from this. And then I'm going to fit this linear model using the LM function. I'm predicting mass, so that's my y variable, using height, so that's my x variable. And so the way that you put in a formula into the LM function is always going to be y tilde x, and then I indicate what data I would like to use. So LM here means linear model. What is beta hat 0, do you think, from this output? Negative 32.5, exactly. So when I run this in R, it's going to give me two coefficients. The first will be the intercept, which is negative 32.5. And what about beta hat 1? What is that? 0.62. And how would I interpret that in terms of these variables? Yes, so one increase, in this case it's centimeters of height, will yield a expected change in mass of 0.62, so an increase of 0.62. So for every 1 centimeter increase in height, a Star Wars character's weight on average increases by 0.62 kilograms. And so the important pieces in this of if you're asked to interpret these values like on a lab, for example, like you will today, it's important that you mention what the units are here, and that you mention what variable is the dependent or the independent variable, in this case height. And then you want to mention something that indicates that this is, you can say on average or expected or estimated, but basically making it clear that this is a model and not an absolute value. So this is on average, weight is going to be increased by 0.62, but of course there's an error term in there. So the general version of this that you can use for any of your simple linear regression models would be for every 1 unit increase in x, the expected change in y is beta hat 1. So again, when you're doing this like for an assignment, you'd want to make sure you're always updating what x and y are to be what they were in your question, as well as be sure to mention something like expected change or estimated change or average change to note that this is just an expectation and not true for every single point. Okay, so the main reason we fit a linear model, kind of mimicking what we did when we were talking about the mean, was the first reason might be to reduce the dimensionality of the data. So for example, and when you have, like our data here has n times 2, we've got n observations and we have 2 data points, or 2 variables here, height and mass. And we want to reduce that to just two dimensions, or just including just 2 values, just the beta 0 and beta 1. So that like dimensionality reduction is very appealing and a big thing that we do a lot in statistics, because instead of needing n times 2 data points, you can just reduce that information to 2. And then similar to the mean, to get a sense of the relationship between x and y for a typical observation. And so when is this going to be an accurate representation of that information? When is a linear model going to be an accurate representation of the relationship between x and y? When the data is linear, exactly. And so I just drew a couple pictures kind of akin to what we were doing when we had the mean. Which lines do you think represent typical observations among these three?
First one.
Yeah, so definitely the first one. This is definitely a linear relationship. I think the relationship here is that y is equal to 2x. I would say also the second one. So the second one, there's not an obvious nonlinear relationship. It looks like there's really just no relationship. So, fitting a line is one way to describe that really there's not a strong relationship between x and y here. So this would also be an okay case for a linear model to try to describe x and y. And the reason why is because if you look on either side of this line, we're not really misrepresenting this data. Like similar when we had the mean and we wanted that mean line to fall kind of right in between the most common data points. Here, if I look on either side of the line, it's not misrepresenting the data in any kind of meaningful way. There's just not a strong relationship between x and y that can be measured. What about this third one? Is this a good case for a linear model? No. It is not. A simple linear regression model is a terrible choice for this. It's basically only going to be correct twice and basically incidentally. So you'll be right if you happen to fall kind of in these two intersection points, but any other time you'll be pretty wrong in terms of guessing what y is based on an x value. Here's a couple more that I thought I would just draw. This is an example of a cubic term, which again, the line is really not a very good representation here. There's really probably more of a nonlinear relationship. Here we have two outlier points or influential points way up here that's pulling the line. So you'll notice like these data points kind of look like they have maybe a bit of a positive relationship, but these 2 points are pulling that line up, making it almost look like it's negative. And so this is an example where there's data points that are kind of overly influential, changing the relationship that looks like it's being observed. So this would probably be a case where a linear model might not be a great representation either due to these outliers. And then this is a case where the data is really split. This is kind of like that bimodal distribution that we were looking at before, where this line is really not representing anybody. And so probably two separate lines or two separate models would be a better way to estimate the relationship between x and y. And so trying to figure out if there's a third variable that helps you dictate which of these kind of clouds the observations fall in and fitting a model stratified by that would be a better choice. Okay, so recap, simple linear regression model is appropriate summary measure when the data is linear. And so the assumptions that need to be true are that the relationship between x and y is linear and there are not any kind of strong influential points that are kind of pulling your model in one way or another, maybe it being overly influencing what you're seeing. Okay, so we're going to spend the last 30 minutes doing the lab. So let's go to that. You can go to the schedule. If you go down to assignment, you can see the lab for today. The top is going to be similar to what you did last time, where you're going to create a new project with my template files, and you're going to change the author name to your name and change the date to today's date. And here you're going to be doing this using the same data that we just were using in class. We're going to use the Star Wars data. And what I want you to do is these first couple exercises are using all of the observations in the Star Wars data set to predict the weight from a character's height. And then these last parts are going to be creating a new data set like what I was using in the slides that removes one of the observations. We're going to remove Jabba from the data and see how those plots and also how those estimates from the linear models compare. So you can go ahead and get started on that, and I will be here to answer all of your questions.